Okay, so I'm from Microsoft Research in Cambridge, and this is some work we've done with various folks in the lab. And this is probabilistic programming for machine learning. So I sort of, slightly by accident, stumbled into what seems to be a hot topic, So, luminaries at great companies like Google and Microsoft are have been venting in public about the significance and importance of machine learning on big data. So there's a quote there from Halvarian. There's all this data out there. What's scarce is the ability to extract actionable information from all that data. And then Craig Mundy, who's CTO of Microsoft, and Eric Schmidt, equivalent sort of top guy at Google, were at the Davos conference in 2011, and they were both at a sort of dinner party and were asked, what's the most important topic? And I think Schmidt was late, and Mundy stood up and said, machine learning. Then Schmidt arrived and said, machine learning. So, wow, machine learning, what can we do about it? And I don't know about you, but I mean, I'm a sort of language geek, and a few years ago, I thought I had next to nothing to say about machine learning. I had no idea what it was about. I mean, we had Anders was here on Monday at in the panel, and he actually said that he agreed that machine learning was like a real hot topic for the industry, but he didn't see what programming languages had to do with it. And I think most of us feel that way. So the point of my talk really is to tell you that there's that ideas in probabilistic programming that have been sort of rather esoteric, for many years, today can be used to express a whole variety of different machine learning algorithms in a declarative way, and then we can have compilers for probabilistic programming languages that take those descriptions, succinct descriptions of the intended algorithm, and turn it into a very efficient low-level code that will do a good job of doing machine learning. So probabilistic programming, it seems to have a lot of potential. It's a way of letting a developer write short programs for a particular modeling task, maybe tweak them a bit if it's not quite right, and all do that in a very declarative style from a small functional program. So that's the idea. Those are essentially the ideas I want to get across to you in the next half an hour or so before lunch. So let's see. If you go read books about machine learning, you'll see that there's this idea of Bayesian statistics is an important unifying principle. So research, the idea about Bayesian statistics is that you've got some sort of uncertainty about the world, and you represent that in a probability distribution. And after seeing more data about the world, you have a conditioned probability distribution that tells you more, and you can use information about the distribution to perform various actions, like clustering documents or classifying documents as spam or not, and so forth. And they use conditional probability distributions, and then if you go and read the research papers, they'll describe these distributions in mathematical terms and using integrals and various diagrams and so forth, and then they'll describe algorithms that can be implemented on top of to actually realize those distributions. But Bayesian researchers tend not to, consider that anyone would actually want to have a language that let you automatically discover those algorithms, or automatically have those algorithms generated for you. And that's the idea of probabilistic programming. So the alternative today is that if a programmer wants to go and use machine learning algorithms, you can go and get various packages that have a fixed set of algorithms. And if they exactly fit the task you want to do, you're great. But if you need some sort of variation, then it can be hard to make use of those libraries. And then the alternative is to write it from scratch, and that you can end up having thousands of lines of code for implementing these things. So that's the problem. And I'm putting forward probabilistic programming as a solution, that we have a succinct model written in a declarative style, and from that we get an efficient, we use a compiler to get efficient inference code. Okay, so a bit of background. You might have heard that Judea Pearl is very recently was announced as being the Turing Award winner for 2011. What did he do? Well, back in the 80s, he was a pioneer of AI during the sort of AI winter, who figured that we could use probability distributions to represent the uncertainty about the world. That he figured that lots of cognitive tasks that humans and animals perform in their brains are actually achieved using probability distributions, and when you learn, you're actually conditioning those distributions. And he proposed that as a way of structuring computer programs that could do inference automatically. In a bit more detail, by the way, these are quotes from the the award citation for Judea. The thing that's most relevant for this talk is the idea of probabilistic graphical models. And this is a standard idea in Bayesian stats that was introduced by Pearl back in 1988. And let me go through the different parts of it. First of all, it's a model. So you use a graphical structure like the ones that are on the whiteboard behind Pearl in that in that picture. You have a graphical structure where the nodes represent random variables in the world, like whether I'm going to have an example later on of Cluedo, where there's going to be two random variables. One is like whether Scarlett or Mustard committed the murder. Another random variable is whether they used a gun or a pipe. And so those would be two random variables in a graph, and you would have edges indicating influences. So thank you. So you would have so there'd be an edge from the individual, who it was, that would influence which type of weapon they were going to use. So that's the model, and it's probabilistic to represent uncertainty. There's lots of kinds of uncertainty. We don't have perfect data. Often there's items are missing. There's various kind of measurement error. You can have noise, and you also are uncertain about exactly how the data arises. You've got various theories about how data has come to be, but they may not be correct. So you can factor all that into. You can factor that uncertainty by representing it using probabilities. And as I say, we use graphs to represent dependencies. And the big challenge that we have when you represent the world as a bunch of random variables is that in principle you get an exponential blow up of number of possibilities. And the other thing about graphs is they can represent the dependence explicitly between variables and the independence implicitly. And if variables are independent, then you don't get the exponential blow up. And Pearl also invented these so-called message passing algorithms that send messages around the graph according to the graphical structure, and can be used to infer conditional distributions. And there's many different application areas in speech processing, vision, robotics, and so forth. And these are actually starting to become real. I mean, this has been a very hot topic in the research world for many years, but over the last 5 years, there's been some really large-scale deployments of these probabilistic graphical models. I've got a couple of examples there from Microsoft. That there's a TrueSkill system that I'll describe in detail later, which is used to rank Halo players in other games in Xbox Live. And there's Ad Predictor is used by Bing to predict how likely a user is to click on an ad. And there's many other examples. I think TrueSkill was the very first large rollout of Bayesian reasoning in large data centers. And there's also smaller scale applications in things like medicine, where the computation can all take place in a single machine. So that's the kind of background that we have, another bit of background is called Infer.net. So this is the research project that's been taking place in the MSR Cambridge lab for the last few years, and this is an example of a probabilistic programming system. You can go and download this from the web. It lets us do probabilistic inference, and it's based on .NET. It uses probabilistic graphical models. It implements a variety of different algorithms. Some of them are approximate, and others are exact, and others are stochastic. You write models using C#, using a particular object model. So let me, this is an example of the kind of rapid prototyping I'm speaking about. But what they don't do is literally use a C# program to represent the probabilistic model. Instead, they have an API that lets you construct a little pseudo program in memory that sort of represents a probabilistic program, and then the compiler takes that sort of object model and then compiles it down to a C# file, and then that gets turned into an efficient algorithm. So this had been going on in the machine learning group for a while. And I'm a PL person, and we're sort of in a different corridor, so we didn't really talk. Hey, that's communities for you. But it's finally dawned on me that what these guys were doing was a very interesting new kind of compiler that could be extremely valuable as we're kind of experiencing the data deluge. And there's statisticians are just being snapped up after they graduate by lots of big corporations that have to make important business decisions, and they need statisticians to be able to get those decisions right. And if they get them wrong, it could be a life or death problem for the company. This is it's really valuable, the kind of information you can get with stats, and they were. So I realized that this kind of programming language could be useful, hugely useful, and moreover that it was a place where people like you and me, language geeks, can actually play a role. And the really lovely thing about this system is that you can understand broadly what's going on without a really thorough understanding of the stuff I had in the previous slides. You remember thinking, what are all these probabilistic graphical models? Do I have to understand all that? Do I need to understand all the integrals that arise when I define these conditional distributions? And the good news is you don't need to understand that. Instead, you can think of these graphical models as programs, and then from there we can build. There's a great opportunity for us to build tooling, to build languages, to build libraries of examples that can be applied to these big problems, and that also that can be tied up to them, because these big data in databases of various sorts. It's in spreadsheets, and it's in huge NoSQL style data center areas. So there's quite a lot of challenges for us to figure out how we can take these kinds of algorithms and apply them at that kind of scale. And when we do that kind of work, we don't actually need to understand all the low-level stuff. We can work at this level of abstraction. So that's repeating it again, that's the message I have for you, that by using probabilistic programming as a way of understanding these algorithms, we can make a contribution. Okay, so the title of my talk was this, that Reverend Bayes meet Countess Lovelace. So another thing I want you to take away from the talk is that I'm proposing a marriage between the Bayesian reasoning represented by Reverend Bayes on the left, and computer programming represented by Countess Lovelace on the right. And in particular, I'm going to use one of my favorite languages, F#, as a way of representing probabilistic programs. I should say, it's hard to bring researchers together. Like I was joking about in our lab. We hardly ever speak, and there's some folks in my lab over there. And we've traveled across the Atlantic. We're talking maybe more now than we normally do. So it's pretty hard to get researchers to speak to one another. And I guess the same problem here is, I suppose what I'm trying to do is take a statistician researcher and get him hooked up with a programming language researcher, which is pretty challenging. I mean, they're both dead, and moreover, he was dead before she was born, so it's hard even to imagine them coming together. But I like a challenge, and I think we're up to it. Okay, so we've been working with the Infer.net team to add F# as a new feature, and we have Infer.net Fun, and this is something that's downloadable. It's at researchmicrosoft.com/fun. You can download that as a zip file. You can look at all the samples. If you're not on Windows, you can still download it and have a look to see the kind of programs that we can write in this style. And so the idea is you write a model in F#, and I'll give some examples in a moment. You can run it forwards to synthesize data, and then run it backwards to infer parameters. And there's a number of benefits there over using the previous object model. But I think I should press on to some examples. Okay, so the example I promised was this murder mystery. So I want to represent a probability puzzle as some code. So let's see. So someone's told me that they think that there's been a murder. Scarlet or Mustard have done it, one of them, and other things being equal, they think there's a 30% chance it was Scarlet, 70% it was Mustard. Moreover, they reckon if Scarlet did it, she'd use a gun with 3% chance, otherwise the pipe. And if Mustard did it, he'd use a gun with 80% chance and the pipe with 20% chance. Now we can write that as a bit of probabilistic code. So the first thing we do is define the variable Scarlet. Done it by drawing. Sometimes use sample, sometimes use random here, but by doing a random sample from Bernoulli 0.3. So Bernoulli 0.3 is just an unfair coin, and the bias is 0.3. So there's a 30% chance that's going to return true, and a 70% chance it's going to return false. So this is indicating the first line of the puzzle. Okay, so it's a sort of non-deterministic program. This is going to non-deterministically return true or false, and it's also probabilistic, so we know the chance of one or the other thing happening. And then the with gun variable is indicating, well, whether it was a gun or whether it was a pipe. And if Scarlet did it, then we draw from a coin that's got a 3% chance of being true, which represents that. and if otherwise mustard did it, we draw from a coin with an 80% chance of being true, which corresponds to that. And if you draw out the probability distribution of the four possibilities, sort of, before we know anything else, it's let's see, you can sort of add them up. The yellow lines add up to 30%, and the green lines corresponding to mustard add up to 70%. So then we also have some information that we found a gun at the scene. So the other feature we add to the simple programming language to represent learning problems is observation. So this is this is about like an assertion that I'm going to say that, or adding a constraint to the program, and I'm just going to assert that a gun was used by saying that the variable with gun must be true. And then I'm going to return Scarlett done it. So overall, this is a program that's going to return a Boolean that indicates how likely it is, or rather, the distribution of that Boolean between true and false is going to indicate how likely it is that Scarlett did it, based on the fact we've seen a gun at the scene. And if you think about the distributions, and what's happened is we've chopped out the probabilities associated to being a pipe. So they've gone, and we're just back with these probabilities here, which I've renormalized. Okay, so this is the kind of program I can give to infer.net or infer.net fun, and it will figure out the probabilities. I'm going to say a little bit about the semantics of this language to give you an idea of how we set things up. So we have an operational semantics it's a relation saying that a program P will evolve in one step to a program Q, and we put a probability on the edge to indicate how likely that's going to be. And the rules for drawing from these Bernoulli distributions are that if you say random Bernoulli of R, then with probability R you get true, and with probability 1 minus R you get false. And for every other program feature, it's deterministic. And so P goes to Q with probability 1. So then, for example, if I write out my program again in a succinct style, you get a series of reduction steps. And so in this particular run, the S variable is false. And so we've taken that transition with probability 0.7. This is the deterministic step. And then here, this is the gun variable G is going to be true. So it has this step takes place with probability 0.8, and then we get to false. So we can say the probability of the whole run is obtained by multiplying together each of the probabilities of the steps. Okay, so the probability of that particular run is 0.56. We also say that the value of the run is false. That's the eventual answer from the run. And then finally, what about conditioning? What about these observes? I've ignored those. I mean, when I had an observe here, I just this final step just took place with probability 1. I went from here to here. So we say that to take account of the fact that we want all the constraints to be true, we say that a run is valid if every time you hit an observation, the Boolean being observed is in fact true. So that's the way we slip conditioning into the language. So a little bit in a bit more detail, we say that overall the semantics of a program is a probability distribution, which is just a function from values, the possible answers of the program, in this case true or false, to probabilities. So and we write it like this. So it's a function that goes from a value v to this probability. So this is, if you remember from school, this is a conditional probability notation. It's saying that the value of the run is v, and we're conditioning on the run being valid. Okay, and if by definition, that just means this, that you intersect the set of runs that return the value v with the valid set, which is just basically saying we're going to throw away any runs where the observations fail, and then we normalize by dividing by the probability that a run is valid at all. So in this particular case, I had my 4 possibilities, and I'm conditioning by the valid runs, and the only valid runs are the ones where gun is true. So we get, say, as the answers to the probability puzzle, this calculation here that say the probability that Scarlett did it is this guy here, which is 0.984. Oh, I've got this wrong. What have I done wrong? Because she's got much less likely to do it after we observed that it was a gun. So the value. So I think I've switched to 2 values. I think I've got these 2 the wrong way around. Because open divided by... Yes, that's going to be very small, and this is divided by the same thing, so that's very big. So sorry, I've got that sort of the wrong way around. Anyway, so beforehand we thought there was a 70% chance that the mustard had done it, and after the calculations, we see there's a 98% chance that he's done it. Okay, so that's a bit of detail. I don't want to linger on that. We have a paper that goes into all the details, but I wanted to just show you from first principles that we can define an operational semantics, and then the interpretation of these observes is as conditional distributions. Okay, so now let me go through some examples of programming with Infer.net Fun. So this is the overall structure that we have. I'm going to give you examples of this, but we have an API. Now, my little example is basically illustrated the main features of the API, that we have a collection of different distributions. So we have this Bernoulli distribution that's for coin tossing, and then we've got Gaussian distributions that's like the familiar bell curve, and a variety of other distributions over more complicated things like vectors and matrices and so forth. And so we have the distributions, and then the API also has this random guide that can make draws from those distributions, and it has observe. And that's pretty much it. That's all you need to add to F# to represent these models. And when I say that's what we add, we also take a lot away. So we need to have conditionals and array comprehensions and records and arrays, those guys, but a lot of other features of F#, particularly ones to do with any kind of imperative behavior, we throw away. So we're using essentially pure functional programs augmented with random choice and also with conditioning. So then I write some models, and I'll give examples in a moment, against the API, and then there's two things you can do with it. One is you can run them forwards to actually get some data, and then otherwise you can run them backwards to infer parameters. And I will show you that on an example of linear regression. Okay, so I'll give you a demo of this, so this is a very simple puzzle, but it gets at the idea that a lot of these machine learning problems start off with a distribution over parameters. But I have a question. Maybe I'll take the question. Very good question. We don't need recursion. No, we omit recursion. So there's no non-termination in the language. We have iteration over arrays, but you don't need to have recursive routines.
I would like to have.
Very well. There are other systems that can give you that. But yeah, I it gets. You know what? You can look at our paper, and when you get the Gaussian distributions in, things get a lot more complicated than the example I just gave you. And we were very happy there was no recursion, because that would be a further headache. Okay, linear regression. Here's the puzzle. I've got some points, some green points there that I think are that I believe come from a line. I want to fit the line. So and the parameters of the line are A and B, where A is the A is the slope and B is the intercept with the y-axis. And so what I was saying was that a lot of machine learning problems have the structure that there's some parameters that you're trying to learn, and initially you have very little knowledge about those parameters, and then after observing some data, you have a much finer view of what you have much less uncertainty about what those parameters are. So in this example, my parameters are A and B, and initially I've got a lot of uncertainty about what they are because I've not seen any numbers, and after seeing the numbers, I have a much better idea. So that's the problem. And I've spoken about going backwards from data to the parameters. The other thing you can do is run forwards. Given the parameters, you can actually generate some data. And that's actually very useful in practice. You want to be able to generate data from some fixed parameters to just practically check out your algorithms to see if they're actually giving you back sensible answers. So that's one thing that's not supported in the basic Infer.net using the C# object model. And that's the thing we get from F#. Because we're using quotations to interpret just ordinary F# code and compile it down to Infer.net, we can also just run that F# code. And that's the way that we get synthetic data that we can use for test purposes. Okay, so demo, I hear you ask. So here's my code. So I have a function point, and I give it x, a, and b, and some noise, and I return a pair x and y, the point. And I compute y by drawing from a Gaussian, whose mean is a times x plus b, and we throw some noise in. So drawing from a Gaussian is basically adding some noise to the mean. So that's what this is doing here. The parameters, so as I say, I've got initially a lot of uncertainty about them. So I say that the parameters are defined by a bit of random code that draws A and B from these Gaussian distributions that have a lot of uncertainty in them. So A has got mean 0 and B has mean 5, but otherwise they're rather uncertain. And we also have a distribution over the possible noise that we're going to add to each point. So this function just defines the prior knowledge that we have about the parameters. And then this model code, this is going to induce a conditional distribution by using observe. So model takes in the actual observed data, the points we want to fit A and B to. We call parameters to choose values A, B, and noise, and then we compute by calling this point routine many times the y coordinate corresponding to each x coordinate in the input data, and then at the level of an array, we observe that the whole array, the input, equals the one I've just generated. So this is like doing conditioning, just as I did in the simple example earlier. I'm conditioning this whole these whole Gaussian distributions based on that observation, and then we return A, B, and noise. So if you ran, say, this forward, it would give you synthetic data, and then if we run it backwards, which we do by some code down here, let's see, where is it? Just do some quotation. So, there we go. Yeah, so here, so model was the function I defined above, and I've got some concrete data, and I call infer fun. So this is calling our library routine, and when we call this, we take the quoted form of model, which is just a bit of functional code, and we compile it to the infer.net object model, sort of eliminating records and eliminating functions and do various other things, eliminating array comprehensions. And then we get back these distributions here of A, B, and the noise. And so what we don't get back is individual floats. We get back distributions over floats. So we get mean and variances for each one of these parameters. And so if we run it, what happens is that the console comes up on my other screen. So, okay, hang on. So that's me running it. So the first thing we do is we compile down to infer.net, and so we actually get the C# representation of the same model. And this is rather more verbose and complicated to write, so we'd rather write it in F#. And then the compiler compiles down to one of these probabilistic graphical models. So I was speaking rather abstractly about Pearl's great discovery, at the start of the talk, but this is the kind of thing you get where you have, so these round nodes are random variables like A and B and the noise, and then the black nodes are called factors, and these represent relationships between nodes such that, for example, that we draw that y there is obtained by drawing a Gaussian with mean being the addition of A times the particular data item that we've got together with some noise. I'm sorry, together with the parameter B. Okay, so this is a graphical structure that sort of represents the program. But this is the kind of thing that Perl was advocating writing, and we would much rather write this as code. Code is a really great way of writing graphs, if you can get away with it. Okay, so let me stop that, and then it will actually do some inference, and it should pop up. Right, here we are. We're actually compiling, and it's put the data into this spreadsheet. So what happened was the true line is the red. So we chose those particular parameters, generated some data from them, and then we want to try and infer back. And so we generated the blue points, and then by running the inference algorithm, we're back to the green line. So there's not very many points, so there's some uncertainty. We're not bang on the original value. But what you find is that as you get more and more points, you get a much better fit. Now you might say, Andy, well, what about least squares? That would be the standard algorithm. And it turns out that this is exactly least squares. The general framework I've proposed to you in this particular case boils down to least squares. So you kind of get that for free from the algorithm. Okay, so I have 10 minutes before lunch, so I guess you guys don't want me to overrun. So I will not overrun. Let's get back to the talk. So that's linear regression. I have a few other examples. There's true skill. Okay, so true skill is how we rank players on Xbox Live so that we can figure out from the games they have played with other players, how good they are. And the idea is that everyone has a skill, which is a number between nothing and 50 with mean 25. and based on the games you've played with people, those skills can get bumped around. So again, so in this case, the parameters of the model are the skills of all the players. And this is a very simple example where I've got 3 players, Alice, Bob, and Sid, and I call a function skill that samples from a Gaussian. And in fact, yeah, here it's giving the mean to be 10. Sorry, just different from different versions of this. So the mean is 10, and 20 is a very gives a very flat curve. So if you actually plot this, plot the Gaussians associated with Alice, Bob, and Sid, you get 3 overlapping bell curves like that. So that's before we've got any data. This is the prior. So really we get some data. So we might, so the idea in true skill is that we're going to, the way we decide who is going to win, you've got to get this idea that the way we write the model is write code that represents the sort of imaginary process that's our theory about how the world works. And our theory here is that if everyone has a skill, and if Alice plays Bob, then the way that if Alice's skill is higher than Bob's, then Alice is going to beat Bob. But maybe Alice had a bad day, or Bob had a particularly good day. So we don't just want to directly compare their skills. We want to add some noise in. So we have this notion of a performance. So performance is a function that takes someone's skill and adds a bit of noise to it. So it's pretty close. It's pretty tight around the player's skill, but it is a bit noisy. So it could mean that someone might, in principle, be stronger than other player, but would still lose against them. And then we add some constraints using observe as before. And so in this case, I'm putting in some constraints that represent, let's say, Alice has beat Bob. So we say the performance of Alice is greater than the performance of Bob, and so forth. Just like in the Cluedo examples, we put these constraints in to represent the observed knowledge about the world. And then we return the three skills, Alice, Bob, and Sid. Now, beforehand, if we return Alice, Bob, and Sid, we'd get the chart up here, where they're all the same. But after making the observations, the Gaussians have shifted apart because Alice has basically beaten the 2 other players. So her skill has sort of shifted to being higher and also sort of thinner. There's less uncertainty about her skill. And Bob has stayed in the middle and Sid has moved down. So that's the basic idea, that you kind of shift the Gaussians around based on observations. And if you download the zip file, we've got an implementation in there, and this is the output of it run on a data set of matches between grandmaster chess players. And in the original paper about this, so this is the skills of all these players, and you notice that over time they're sort of getting better, because as on the x-axis is the IDs of the players, and the older ones got to play first, and so this has been compared to the standard ELO system in the original paper about true skill, and it's very very effective compared to that. But it has the advantage that unlike the ELO system, true skill gives you an uncertainty in the outcome. So that's like how wide or thin the bell curve is. And the code for doing this in F# just looks like that. I'm not going to go into all the details, but we have the performances before, and then this is code that is using arrays rather than just three examples. So the prior here generates the skills for each of the players by calling this function here that uses these array comprehensions, and then here we've got the actual observed matches, and that information tells us who plays who, and we've got an array of representing the skills of each player, and then we compute the performance, or the difference between the performances of the 2 players, and get a bunch of results. And then at the top level, we have an observation that says that these predicted results actually equal the concrete data. Okay, I'm being told to wrap up, so I will draw to a conclusion soon. Okay. So that's true skill. And then there's topic modeling. It's a completely different problem area. So this is the idea that so what we want to do is automatically find themes in big collections of documents. And if we can do that automatically, then we can organize them in different ways. So this has been applied to the corpus of documents from the New York Times, and they could discover documents that related to different things, like I think the Korean War, or different kind of political questions and so forth, can be automatically discovered just by looking at the text of the the text from that corpus. And this particular algorithm is called latent Dirichlet allocation, and it's a classic algorithm in probabilistic graphical models. And the idea is that each document is drawn from one of several topics, and a topic itself is just a distribution over a vocabulary that's going to favor some words more than others. So a very baby example here is that I've got some documents called cats, and dogs, and those are the file names, if you like. And then you've got the bag of words. And you've got sort of catty words in the cats document and doggy words in the dogs document. And then the cats and dogs document has got a mixture of both. So it's a very simple example. And so the problem would be, given this data set, figure out what the topics were. And in this case, there's going to be two topics. And in fact, our code, this is a screenshot from running the code, infers there are two topics. And the chart on the right is showing how the words, the sort of doggy words are much more likely to be in the red topic than the blue topic. And then there's some, well, actually, yeah, this is maybe a bit of a biased, this is a very simple example, in fact, but I hope you get the idea. And then we can write the generative process as F-sharp code. And I find this very illuminating. I mean, admittedly, it may maybe take a few minutes to sort of get it if I haven't seen this before. But, it's a very simple, basically, you go look at the papers on LDA, and they'll write down this generative process in words. And then they proceed to figure out, okay, what you're going to have to do is do this fancy message passing algorithm on the graphs. And what I love about this setup is that you just write the code. You take the generative process that people were writing about anyway, and then just write it. And I don't have time to go into it, actually. But if you download the zip file, you can inspect this and see how it basically just corresponds to the standard ideas of topic modeling. Okay, so Infer.net and Infer.net Fun are not the first of these probabilistic languages. There's been quite there's been a bunch of them. I would say these are all out in the long tail. These are not like widely used programming languages. They've been in the research community. The one that's maybe closest to what we've done in F-sharp is called Hansai, that uses OCaml. But that work was limited to discrete distributions and, say, can't handle Gaussians or these Dirichlets and these other distributions. And in fact, it doesn't use probabilistic graphical models as the back end. I do encourage you to download the distribution. I've done that 3 or 4 times now. There's a bunch of examples there that you can look at. Do share the love. We were trying to bring it together with Reverend Bayes and Countess Lovelace. Share the love with us. Download it, have a play with it. We think if you like F-sharp, I think you'll love this. It's really fascinating, and you can really rapidly come up with new machine learning algorithms. What about challenges and opportunities? Well, I think in the afternoon we've got to talk about R. So this is kind of like the background. I think at the moment, probabilistic programming has no market share at all, right? So this is a chart from this Kaggle website. So Kaggle is a startup that's a kind of, they're trying to create, it has a series of competitions or machine learning competitions where they encourage data scientists to come along and participate and, given a data set, infer information from it. These are, the histogram is the number of users using different languages, and so R and MATLAB and SAS are very popular. I'm afraid that at the moment these probabilistic programming languages have made no impact on this. So that's a challenge. I also see this as an opportunity because there's a lot of data out there. There's even more data coming along. I mean, as I said earlier, statisticians are just being snapped up. They're becoming very expensive. So if we could find easy to use ways of doing machine learning using techniques like this, then I think we could really make an impact on that. Because I think at the moment, using tools like R and MATLAB, they're great for specialists like the folks who are competing on this website, but really want to kind of reach out to a larger audience. We're sort of looking for the sort of visual basic of probabilistic programming languages. You're looking for an environment that would have great tooling, would let you see the histograms of data, let you see the effect of conditioning. It would let you easily write your model, but also test it in various ways. That's the thing we're trying to build. So that's, I think, the big opportunity. And I will conclude with a final summary slide. And maybe Matt will let me take a question or two. So thanks for your attention.